we discussed the definition of topology on a general set on an arbitrary set X in the last segment. In this segment, we'll get started with the definition of subspace topology. So let me define subspace topology first. Subspace topology. Let S, tau be a topological space and A be a subset of S. Okay, so this is a topological space, meaning that tau is a collection of subsets of S which satisfy all the properties we described in the definition of topology on a set, and this pair is called the topological space. And now we are given a subset A of S. So how can we define a topology on A? Okay, so let's see how we do that. Define tau A to be the collection of subsets. Okay, so meaning that we are looking for a collection of subsets of A. Okay, that is denoted by tau A, and this is given by intersection of U and A such that U belongs to tau. Tau is the topology on S. Okay, so you choose all those open sets from the topology on S and take their intersections with the given set A. So the collection thus formed by taking all the intersections constitute the topology on A, which is called subspace topology. So let's observe that this is indeed a topology. This collection satisfies all the properties of a topological space. So by the distributive property of union and intersection, okay, so you learned this distributive property of union over intersection and distributive property of intersection over union in basic set theory. Let me recall it for you. So if A, B, and C are sets, then A union B intersection C is equal to A intersection C union B intersection C. Okay. Right. And also A intersection B union C is the same as A union C intersection A union C intersection B union C. Okay, these are the distributive properties. So using these properties, we see that the union of these sets, okay, is the same as this union intersection A. Okay. follows from this. Okay, it's a generalization of the first distributive property, right? Okay, and we also see that for a finite collection, okay, this also holds. Okay, so what does it mean? It means that if we take an arbitrary collection of such sets, okay, then the union of that arbitrary collection can be written like this, okay, and this guy is also in the form of this one, right, where A is this one and this guy is again an open set in tau. Why? Because U alpha is an arbitrary collection of open sets in this topology, and the union of this arbitrary collection of open sets is again open. Okay, we already know it from our discussion of the first segment. Okay, so this guy also belongs to this collection. What does it mean? It means that this collection is closed under arbitrary union. Okay, this collection is closed under arbitrary union. That's what we have found here. Now, if we have a finite collection of elements like this, okay, that we have written down here. So now the intersection of such a finite collection is again in this form, where A is this set and this guy. So we're talking about a finite collection of open sets, okay, and the intersection of a finite collection of open sets from tau is again open. From the topological property, from the standard definition of a topological space, we know that this guy is an open set in tau, which belongs to tau, and an open set intersected with A also belongs to this family, which means that this collection that we are defining is also closed under the intersection of a finite collection. Okay, it is closed under the intersection of a finite collection of elements from here. It proves that this guy is a well-defined topology on A. Okay, all right. Now, so we have seen from our previous discussion that tau A is closed under arbitrary union and finite intersections. So it's better finite intersection. Okay. And moreover, so we have defined tau A to be this collection, right? U intersected with U such that U belongs to tau. Okay, where S tau is the given topological space. Okay, so now besides, one also see that this empty set empty is in tau A. How is that possible? Because empty is in tau, okay, from the definition of topology. Okay? Because this is a topological space, so empty set should be in this collection. So now by the definition of tau A, this guy has to be there, right? And what is this? This is empty. So this empty set is in tau A as well. Okay, now another observation, A is also in tau A. Okay, and how is that possible? Because S is in tau, by the definition of topology, the entire set has to be in the topology. Okay? So S intersected with A, this also has to be in this collection. And what is it? It is A, because A is a subset of S. So A is also in this collection. So that confirms that indeed tau A is a topology on A called subspace topology of A in S. Okay. Now let me give you an example of subspace topology. Consider the subset A, the closed interval from 0 to 1 of R, the real line. Okay. Okay. So in the subspace topology, the half open interval 0 to 1/2, okay, is an open subset of K. Okay. What does it mean? So we are taking this subset A of the real line R, and we are trying to give A a topology with the use of the topology the usual topology of R. Okay. You see that 0, 1/2 in R is not an open set. It's a half open interval. It's not an open set in R, but it's open in A with respect to the subspace topology. Why? Because you can put this guy in this form. Let's see how. You can write 0, 1/2 as -1/2, 1/2, which is an open set U in the topology of R, because it's an open interval in R, so it's an open set in R, intersected with the set, the underlying subset. What is the underlying subset? 0, 1. So this can be seen more clearly if we draw a picture, the picture of number line. 0 is the origin, and say this is -1, and on the right at the same distance we have +1, and this is say -1/2, and this is +1/2. So this is 0, 1/2, the half open interval in R. Okay. And what is -1/2? +1/2 is this interval, which is an open interval in R. And this is the subset, the underlying subset of the real line, 0 to 1. Okay. So what is the intersection of this with this? Is this shaded interval, right? So I think I made a mistake here. It has to be open. Okay. So this can be written down as the intersection of -1/2 to +1/2 and 0 to 1, the closed interval, which is clear from this picture. So this guy, of course, belongs to this collection, and hence is an open set in the subspace topology of A in R. Okay. Alright, so this was the example of subspace topology. Now we move to the discussion on basis. Basis. So here is the thing. We have this huge collection of open sets in a given topology. Okay, so we are given a set first, and we write down a collection of all possible open sets of that set, and that constitute the topology. So often it's cumbersome to describe, to write down or describe all the open sets of the given topology. So we need a basis, so which is a subcollection of these open sets of the given topology. So smaller number of open sets that somehow describes the huge collection of open sets, in the sense that if you choose any open sets from your topology, that can be written down as a union of this union of elements from this subcollection, and that subcollection is called the basis of the topology. Okay, so let me explain a little more rigorously. So let me write down the definition. A subcollection so here we have this topology S comma tau. So tau is a collection of all open sets of S, but we are aiming, so our aim is to find a proper subcollection, which we will denote by this calligraphic B. Okay, and so let's see how it turns out. A subcollection calligraphic B of a topology tau is a basis for tau if given an open set U. Of course, this open set U belongs to this collection. Okay, and the point P in U. So you are choosing a neighborhood of this point P in this topology. Okay, so an arbitrary open set you are choosing from this collection, and which of course contains the point P. There is always an open set B in this subcollection such that P is also in B, and B is contained in this open set U, meaning that it should be something like this B. So it happens for all the points of this open set U. So first you choose an open set from this collection of open sets in your topological space, and then for any point P in U, you should be able to find an element from this subcollection such that P also belongs to this element of the subcollection, and this element of the subcollection is contained in your open set. Okay, and then this subcollection is called the basis, okay, for the topology tau. An element B, see that an element is denoted by the Latin B, and the subcollection is denoted by this calligraphic B. Okay, so an element Latin B is called a basic open set, okay, which is an element of the basis of the topology. Example. So here is an example, the standard example. The collection of all open balls B, P, comma R, which means that this ball is centered at P and it is of radius R in the standard topology of R to the n that we discussed in the last segment, in the beginning of the last segment, with P being the center, a point in R to the n, and R is in the set of positive real numbers, which is nothing but 0, infinity. So the collection of all open balls is a basis for the standard topology, that is also called the metric topology of R to the n. Okay, so in the standard topology of Rn, there is a huge collection of open sets, but we're not going to take all these open sets. We just take a subcollection of the open set consisting of all open balls. And this subcollection forms a basis for this metric topology on Rn. Okay. Okay. Now we have a formal result put down as a proposition. So our first proposition of this lecture, proposition 1. A collection calligraphic B of open sets of S is a basis. So I'm not writing explicitly that S is a topological space, but it is implied that it's a topological space. Is a basis if and only if every open set in S is a union of sets in this collection B. Okay, so here is the proof. So first we prove this direction. Okay, so you break down this if and only if with this both-sided arrow. So now we are going to prove this direction. So we are given a collection, in fact, well, let me write it as a sub-collection. Okay, we are given a sub-collection B of open sets of S that is a basis. What does it mean? So if you divide this statement into two parts, one is prior to this arrow, which is on the left of this arrow, which says that a collection B of open sets of S is a basis. Okay, so we have written down this fact here, and this is taken to be true. Okay, this statement is taken to be true. Now we have to prove that whatever is left on the right side of this arrow is also true. that needs to be proved. Okay. Okay, let's prove this thing. Every open set in S is a union of sets in B. This needs to be proved. Okay. And this is taken to be true. This is the hypothesis. U is any open set in S. Okay. Also, let P be a point in this open set U. Okay. So U is which means that U belongs to tau. Okay. Okay. Since this subcollection calligraphic B is a basis of this topology tau, there is a basic open set BP in this subcollection B such that B is in B sub P, where B sub P is contained in U from the definition of basis of a topology. Okay. We defined it earlier. Okay. So let me draw a picture for you here. So here is this open set U, you taking P a point of this open set. Right. Now, by the definition of basis, there is a basic open set BP that contains P, and this BP is contained in U, the first open set that we started with. Okay. So now you can immediately see by set theoretic argument that the union of all these basic open sets, as you vary P in this open set U, so not without, so say that we choose another point here, and take the corresponding basic open set. Okay, as we move along other points of this open set U and take all the unions of those basic open set, and that has to be a subset that has to be contained in U. Similarly, one can show that U is contained in the union of these basic open sets for all points in this open set. Okay, and that establishes the fact that U is indeed equal to the union of all these basic open sets. Okay, so I want you to convince yourself that this is true. Convince yourself. It's very easy to see, okay? But I leave it as a small exercise for you. Okay, so every open set, so we have chosen an arbitrary open set U from the topology tau, and showed that that can be written as a union of basic open sets. Okay, these are elements in this subcollection calligraphic B. Okay, so this is how we prove this direction. So let us prove the other direction. So now we are going to prove this direction. Now we'll be assuming that every open set in S can be written down as a union of sets in this collection, and then we have to prove that that subcollection of open sets is indeed a basis of the topology. Okay. Suppose every open set in S is a union of open sets in the subcollection calligraphic B. Okay, suppose this holds. Now, given an open set U and a point P, in U, okay, since U is an element of tau, okay, or in other words, U is an open set in S. So it must be possible to write U as a union of basic open sets. That's what we have written down here. So these B alphas are elements in this subcollection. This is something that we are writing by the hypothesis. Okay. So since this is true, there is a B alpha in this subcollection such that P is contained in that element of the subcollection, and well, U is written as a union of all these elements, right, of the subcollection. So each of the elements in the subcollection, or sorry, each of the elements in this union is contained in this open set U, right? So P belongs to one of these elements, and that element is also contained in U. Okay, so thus it verifies the fact that this subcollection is indeed a basis of the topology tau. Okay, hence B, this subcollection is a basis. Okay, QED. Right. So the next topic that we want to discuss is called second countability, and second countability. Okay. So after understanding what it means by second countability, we'll understand what it means by a second countable topological space. Okay. All right. So before that, we need some results, and we need to fix a few notations and we have to fix a few terminologies as well. We say that a point in Rn is rational okay. So we have a point, say P in Rn. Okay, what does it mean? It has n coordinates. Okay, so P can be written as an n tuple, right? P1, P2, all the way up to Pn. And this point is called a rational point if all these coordinates are rational numbers. Okay, this is what we mean by a rational point in Rn. Okay, let this boldface Q denote the set of rational numbers and this boldface Q plus denote the set of positive rational numbers. Okay. So for a rational point, each of the coordinates is a rational number belonging to this set. Okay, now we have a lemma 1, which states that every open set in Rn contains a rational point. Okay, how do we see this? So here is the sketch of the proof. Okay, an open set U in Rn contains an open ball BP, R. Why? Because we have already discussed that the collection of all open balls is a basis for the standard topology on Rn. Therefore, if we choose an open set U in Rn and P is a point in U, then BPR is contained in U. We can find such an open ball, of course. Okay, and this guy BPR in turn contains an open cube. Okay, where length of this cube I sub I is the open interval pi minus r over square root of n pi plus r over square root of n. Okay, so each of this length is given by this open interval. Okay, where I runs from 1 to all the way up to n. Okay, so how to see this in two dimensions? For the case of R2, let's see. Okay, so consider an open ball in R2. So let me draw the picture for you. Okay. Now 45-degree, I'm going to draw this diameter. Okay, and now I can fit a square inside this circle, right? This diagram is not going to be an exact one, but you know, it should make sense. Okay, so the length of this diameter is 2r, so that 1/2 of this diameter is r. Okay. So now tell me one thing: if the sides of this square is given by a, then what is the relationship between a and r? By Pythagoras, we know a square plus a square is equal to 2r square, which is 4r square. It means that 2a square is 4r square. In other words, a is equal to square root of 2 times r. So we have seen that a is equal to square root of 2 times r. So if the coordinate of this point P is P1 comma P2, okay, then find out the coordinates of these 4 points. So the coordinate of this guy is P1 minus half of the length of the cube, okay, that is 1/2 of a. This is 1/2 of a, which is r over square root of 2. So this is P1 minus r over square root of 2 comma 0. The coordinate of this guy is 0 comma P2 minus r over square root of 2. The coordinate of this guy is P1 plus r over square root of 2 comma 0, and the coordinate of this guy is going to be 0 comma P2 plus r over square root of 2. Okay, So this was the situation when n was equal to 2. Similarly, you can draw a diagram for the n equal to 3 case as well, and there you will see that this summand turns out to be r over square root of 3 for n equal to 3. Okay, you can check. I'm not going over the n equal to 3 case. Okay, now back to the general n, back to the general case n, back to the general n case. For each I, let qi be a rational number in ii. Remember what ii was? I sub I was an open interval. Right? I sub I was this open interval, ei minus r over square root of n, and pi plus r over square root of n. Okay, so we can always choose a rational number in this interval. By elementary real analysis, we know that this is always possible. Okay, so we choose qi to be that rational number in this open interval ii. Okay, so that q1, q2, all the way up to qn is a rational point. You know what it means by rational point, we already discussed. Okay, it's a rational point in the product of these intervals, in other words n cube. Okay, which by our description is contained in BPR. In the two-dimensional case, this BPR was this open ball, or open disk if you want to say. Okay, so therefore we have found that Q is in this cube, n cube, and this n cube is contained in BPR, and this BPR is contained in U, the open set that we started with. Okay, so it establishes the fact that every open set in Rn contains a rational point, QED. Okay, now moving to the next result, proposition 2. The collection calligraphic B sub RAT of all open balls in Rn with rational centers and rational radii is a basis for I to the n. Okay, so here is the thing. So we don't take all the open balls. We don't take all the open balls that of course constitute a basis of R to the n. You only take all the open balls with rational centers and rational radii. Okay, so if we choose an open ball P comma R, P has to be a rational point and R has to be a rational number, and the collection of all such open balls constitute this collection P sub RAT. Okay, so now this is what we need to prove. Okay, proof. Given an open set U in R to the n, okay, and P in U, there is an open ball, okay, P comma R prime with positive real radius R prime such that P is in BP comma R prime and BP comma R prime is contained in U. You all know this, right? Here B is any point, right, in this open set, and R prime is a positive real number. Okay, this is well known. Now take R, take a rational number, take a rational number R in 0 comma R prime. Okay, you can always do that by an elementary result from real analysis. So if you do that, then one can immediately see that P is in BPR, okay, where R is that rational radius, and this guy is going to be contained in BP comma R prime, since R is a rational number in this open interval 0 comma R prime. So this ball is going to be contained in this ball, and BPR prime is contained in U, of course, by our previous argument. Okay. Now, by lemma 1 that we proved a while ago, we can say that there is a rational point, in the even smaller ball B comma R over 2. Remember, R was the rational radius. Okay, so if we divide it by 2, that is also going to be a rational number. Okay, so by lemma 1, so P comma R over 2 is an open set in Rn, and by lemma 1 it must contain a rational point. Okay, so let us call that rational point Q. Okay, now what is the claim? We claim that P is in BQ comma R by 2, and BQ comma R by 2 is contained in BP comma R. So this is the claim. We have to prove this. Okay, let's try to do this first. Okay, so before doing that, I need to draw a diagram. So here is the diagram. This center is B, and we are calling this radius R. Okay, so that this ball, it should be an open ball. It has to be a dotted one, but you know, I did not do it. It's easier to see a solid sphere. BP comma R. Okay, and so if I draw another ball centered at B and of radius R over 2, say this is gonna be something like this, okay? Then inside which there should be a rational point that we are gonna call Q, okay? So now if you choose Q to be our center and R over 2 to be a radius, then we are going to have a smaller ball like this. Okay, this is going to be BQ comma R over 2. We have to show that P is contained in this smaller ball, BQ comma R over 2, and BQ comma R over 2 is contained in this bigger ball, BP comma R. Okay, this is what we need to prove. Okay, let's see how the proof goes. Since the distance between P and Q, okay, the distance between these 2 points is less than R over 2. Why? Because I chose Q to be the point. I chose Q to be the point in B comma R over 2. Remember? So the distance between P and Q should be less than R over 2. Okay, this follows from the definition of open ball in the standard topology of R to the n. So from which it follows that we have P to be inside BQ comma R over 2. So since the distance between P and Q is always less than R over 2, if we choose Q to be our center and draw a ball of radius R over 2 centered at Q, P has to be in that ball. Okay, this is obvious. So this part is done. Now we need to prove this containment. Okay, in order to do that, next choose X to be in this ball BQ comma R over 2, then there is something called triangle inequality, which is one of the properties of a metric, which tells you that so if you are not familiar with with the study of metric spaces, just think about it this way. You choose 3 points in your set, say Q, P, R. Okay, so you can think of it in terms of a triangle as vertices of a triangle. These 3 points as vertices of a given triangle. Then you see that the distance between Q and R is this arm of the triangle is less than or equal to the distance between Q and P plus the distance between E and R. This is how you read the triangle inequality for the property of a metric. Okay, so D is a continuous function from, in the metric space. If your metric space is X, then it's a function from X cross X to R plus, satisfying various properties, and triangle inequality is one of them. Okay, so it's easier to understand it in terms of a triangle, and this is why actually it's called a triangle inequality. Okay, so in our case, this is the situation. Then we can write the distance between X and P to be less than or equal to the distance between X and Q plus the distance between Q and P, using this triangle inequality for the 3 points X, P and Q. And the distance between X and Q has to be less than R over 2, because X is in this ball, and we know that the distance between P and Q is also less than R over 2. So it confirms that the distance between X and P is less than R, which means that X is in the ball centered at P and of radius R. Okay, so we have started with X being in this ball, and we ended up with the fact that X also belongs to this ball, which proves that the ball Q comma R over 2 is a subset of P comma R. So this proves that this former ball is contained in the later ball. So which proves our claim. Okay. So what did we prove then? We proved that hence we proved P is contained in B Q comma R over 2, and that is contained in the open set that we started with, U. Okay, so we started with a generic open set in the topology, and we chose a point in that open set, and we have shown that there exists an open ball with rational center and rational radius, such that P is contained in that open ball, and that open ball is contained inside this open set U. That means that the collection of open balls with rational radius and rational radii, um, uh, the, the collection of all open balls with rational center and rational radii forms a basis for R to the n. Forms a basis for R to the n in the standard topology. Okay. We take a break at this point, and then we'll get back to the definition of second countable topological space in the next segment. Thank you for attending the second segment.